Okay, just a second, and I will start the streaming. Okay, so we are live now. Sorry about the inconvenience. Okay. Okay, so we are also live on YouTube now. So as I said, I will first tell you about the model subset command, which is basically used to put one piece of the model at a time, specifically in the specific time in the analysis step where you decide to put that model. Then I will focus on how to apply loads and constraints, because one main point that you have to keep in mind is that if loads and constraints are applied on different model subset, they should be modeled separately. This is pretty obvious because if you want to apply a load on a piece of domain that is not yet into the analysis, of course, OpenSees will give you an error. So this one is a second point you have to take care of. And then there is the concept of initial strength field, but I will explain all this point when we arrive to that point, okay? So I will first start to model. I will do something. I will show you what is the incorrect way of doing it, and then I will correct the error that I will make, okay? So let's start with STKO. And in this case, we are going to do a two-dimensional analysis. So we can go into a orthogonal view and in the XY plane. Just remember that in OpenSees, whenever you want to do a 2D analysis, you should be on the XY plane, okay? Because OpenSees, whenever you have to do a two-dimensional analysis, simply neglects the Z coordinate, okay? So you are forced to draw into the XY plane. Okay, so basically, I will model everything in Newton and millimeters, okay? Now, everything will be elastic because I don't want to focus on linear properties. I just want to focus on the modeling techniques. So linearity and non-linearity does not play a role. The concept is the same, both for linear and non-linear models, and both for static and dynamic, okay? So let's first start with the geometry. I will start drawing a rectangle here because I want to do a soil domain, which is 10 meters. Well, first of all, since I want to model in millimeters, the first thing that I want to do is to increase my grid size to 100 units each one. Okay, so I will start here at minus 500. Here. Plus 500 here, and also 500 in height, right here. So it is 10 meters times 5 meters. Okay, then we are going to create so this one will be my soil domain. Then I will be doing another rectangle up here, another 0.5 meters, so up to here. And here I will have a foundation of 6 meters. So I need another rectangle. Then you will understand why I'm doing all these drawings from here to here. Okay, so basically this rectangle here will be my foundation. Then I'm going to draw the rectangles for my columns that start from here. And it is 2.5 meters, so up to here. Well, actually, a couple more because I need to draw also the beam. .5 here, and then the beam will be 200, so up here. So same thing on the other side. Then I will need a beam up here of 200 units of height. This is perfect. Now, since we want to do a structured mesh, keep in mind that every time you want to do a structured mesh, all these lines should be projected through the entire model. So I need another rectangle that goes all the way down to here. And same thing on this other side. Oops. So now we have basically all the drawing for the soil domain, the foundation, the first structure, which is this portal here. And then, as I told you in the beginning, we want a third column, which is this one in the middle, because we want to do a third stage of the analysis, okay? So I'm going to draw a column in the middle. So once again, another rectangle. This time, just to be symmetric, I use only 200 units. All the way down to here. Perfect. Now, basically, every time you have a grid of lines like this, it is very easy to convert them into surfaces just by using the planar surface command, which is this one, planar. You just need to select all the lines and then right click. Now, as you can see, basically here, I have created a shell, so a compound of faces. But yet I have all the lines that I draw previously, and they are not selected because I don't need them. So I will just remove them by pressing cancel. Okay. So now what I have is just the shell element here. These two are actually holes, so I can remove them. How do I remove a piece of a geometry? Just a piece. I just need to go into the subgeometry selection. So I switch off this button here. This button, as you can see, is saying select the entire geometry. You switch it off so you can select sub pieces of the geometry. In this case, I want to select this one, and I just press cancel. Okay, so I can get rid of them. So basically now we have all the drawing for our structure. So it is fine for our CAD modeling. Then I will start doing all the rest. Now, for the moment, let's save it. And I will use, but of course, I will show you two ways of doing the same thing. The first one, which is the standard way in OpenSees, we will see that the first one that I will show you is fine, but will give you some problems in certain circumstances. And so we propose an alternative solution. I will do it later on. So let's create a first folder called test01. And I can save this file as test01. Perfect. Okay, now basically, now that you have the entire model, as I told you before, we are not going to add the entire model all at once, but we need to use a model subset command. Now, in order to do that, the first thing that we need to do is to identify the selection sets that defines the different pieces, okay? So the first thing that I want to do is to create a selection set for the soil. So once you click here and click add, then STKO says, please select the geometry of the interaction that you want to include. Now, in this case, I want to include all the faces. So let me just go into sub-selection of faces only. And I select all the faces of the soil plus these two pieces here. Right click. And I call this one set 01 soil. If you want to double check if your selection was fine, you right click on the selection set, you click select, and you must see that it will select exactly what you want to include in the selection set. Okay, now we'll do the same thing for the second piece of my model, which is my frame structure without the inner column. So once again, add a new selection set. And also here, I need only faces. So I can select all of them, everything but the inner column. So I need this one as well, and the top beam. Right click, and this one will be set 02 frame. And then I need the third set, which is basically just made of this face here. Right click, set 03 column. Okay, so now we have our geometry and all the selection sets that we need. Perfect. So now we can go on with creating definition as usual. As I told you, we'll do a static analysis. So I just need a linear time series. So I click on definition, add, and I call this one ramp. I go in model, I choose time series and linear. Perfect. Now we can go in physical properties. So we start defining the constitutive models. Once again, as I told you, we are just going to do linear analysis, linear elastic analysis. So the first thing that I want to do is to add the soil material. So we can call it soil. And I go into the material, ND, other ND materials, linear elastic, elastic isotropic. And it will be 1,500. There's some delay with my keyboard here. Okay, and then 0.2. Sorry, for some reason I have some delay in my keyboard because I'm on a remote desktop. Just a second, I want to understand what's going on. Okay, 0.2, 15,000, perfect. I can clone this one and I do the same for concrete. Edit, and I call this one concrete. And it will be 30,000. Sorry for this delay, I don't know what's going on. There is a delay, probably due to the connection. Okay, this is fine. I think we have some questions here. Yeah, but I don't know if it is the keyboard itself because the text is fine, just the numbers. Yeah, it's just the numbers. So let me see. Okay, so here we are. Okay, this is fine. Now the next stage is just to assign them. Okay, so let's go into sub-selection. And I want to select all the phases down here to assign the soil material model. And then all the phases up here for the concrete. Okay, this is fine. Now the finite element model that we want to use. So let me go back into element property. And this one will be just a quad element. And in this case, I want to use a quadrilateral element in an enhanced quad, which is slightly better for performance. I will start with a plane strain condition. Then I will show you some tricky situation when you want to use a plane stress. So let's start with a plane strain, thickness of 1. And I select all the phases and drag and drop. Okay, so that now we have both physical properties and element properties. Now we can go into the conditions. Okay, so we go into condition. Perfect. Now the first thing that we want to do is to apply the fixities. Now the first one will be fixed at the base. And it will be model, constraint, single point constraint, fix, 2D is fine, UX and Y. And I want to apply it to all the lines at the bottom. Okay, so everything at the bottom is fixed both in X and Y. Then I do the same, fix size, constraint, single point, fix. This time only the X displacement will be fixed on the lateral side of the domain, here and here. Perfect. Well, now the third stage will be to add some load. Now, as you know, I want to apply self-weight, and as you know, the self-weight can be added directly into the element. But I don't want to do that, because if you add it to the element, it will be applied instantaneously. Now, in this case, I want to show you the effect of the load increasing in a linear fashion. So an alternative way is to use equivalent nodal loads. Unfortunately, STKO has this ability to assign distributed load, and then it automatically converts these distributed loads into equivalent OpenSees nodal loads. So the second stage will be the third condition will be the soil weight. Okay, model, loads, force, and phase force, because we are using surfaces. So this load will be actually a force per unit area. Now for the soil, we're going to use in the y direction minus 1.5 E minus 5. It's strange that only the numbers are not working. Okay, we'll use the number on the other side, that's fine. Okay, and I need to assign to all the phases down here and here. So this one is the first vertical load distributed on the faces. Now later on, I will need to assign loads also on top of the beam. Now I can assign also the self-weight on the structure, but I don't want to, because it's easier to show you the stress state, and this is my main focus, if I do not assign a self-weight to the structure. So the only other condition that I will assign is a force load. We have some new participants. Okay, is a force load applied on the top edge of my structure. So I will call this one floor weight. I will make it actually, I will not use real numbers now. I will make it very small compared to typical floor loads, just because I want the stresses into the structure to be quite similar, comparable to the stresses on the soil. So it will be slightly small. So in this case, load, force. This time will be an edge force, because I want to apply it on a line. And in this case, it will be a force per unit length. And this one will be minus 0.001. Okay, it will be applied here. And then I need to apply another one, and I will explain you why. I need a second load that I will apply at the third stage. Okay, so once again, if I go back to my drawing here, the first stage is just about the self-weight in the soil. Then I apply the first floor weight here, and as you will see, the stresses given by this floor weight will go only on these two columns, because of course the column in the middle is not yet in the domain. And then I will add the column here, which will not carry the load given by the first floor load, but then I will apply a second floor load, and this second floor load will be carried by all the three columns, okay? So that's why I'm going to create another floor load. So once again, I can just clone it. Floor weight. Number 2, and this one will be the same, but 10 times larger. That's fine. Okay, so we have it. Just let's make sure it is properly assigned. This one is fine, and this one is fine as well. So now we have all the boundary conditions. Now we can start with the analysis. So first, let me save it. Okay, now as usual, the first analysis step that I do is a recorder. And I go into recorders and PCO recorder. So let's give it a name, test 01. And here I just need displacements and material stress. This is the only two things that I want to show you. Okay, then we will add the boundary condition that will act from the very beginning. So add boundary conditions, model, pattern, add pattern, constraint pattern. Okay, so now here we have two boundary conditions, the fixity at the bottom, fixed base and fixed sides. Okay, and okay. Now, as I told you, if I go back here to my presentation, first point here was loads and constraints on different model subsets should be modeled separately, actually, and they should be added just after the model subset. As I told you here, this is the default way you have seen doing my models in all our webinars. This is fine, but if you do not specify the model subset, the entire model will be built since from the very beginning. So actually, before adding the constraint, I need to do an extra step. So I go here and I can call it stage 01, add soil domain. I go into model and you can find it under the miscellaneous command, model subset. Now, how does it work? It has just one attribute, which is called selection sets. And here you can select one or more selection sets. Okay, so all the nodes and the elements contained in the selection set will be part of the model now. Okay, so in this first stage, I just need one selection set, which is the one I called set 01 soil. Okay, so basically, what does STKO do? If you do not specify in the entire model stages no model subset, STKO will use the default behavior. So it will put all the elements since from the very beginning. But if you specify at least one model subset, then all the other pieces will be added only if you use other model subset, okay? So once you use the model subset, the construction of the model should be done explicitly. So here, the first thing that I do, as I told you, is a recorder. Then I add the soil domain. Then I add the boundary condition. They can be added together because, as you can see, both of them are acting on the soil domain. So it is fine if I apply them just after this model subset command, okay? And also here I can apply the self-weight for the soil because the soil has been built at this point, okay? So I go here, add, and this one can be add soil weight. It is still a pattern, add pattern, but this time it is a load pattern. I choose the linear time series, so the load will increase linearly. And I make room for one and I select the soil weight. Perfect. Now we have everything for the soil domain. Now we can just do our first analysis. So click on add, analysis 01. We go in the analysis command, static, plain constraint is fine. This is everything is fine. I don't need Newton because actually it is a linear analysis, so I can just use linear. Then I don't care about the test command because when you use a linear algorithm, the test command is not useful. It is a load control, it's fine, and then I can use 10 time steps. Actually, it is not important that the number of 10 steps because the solution is linear. I'm using 10 just to show you the animation, okay? But in this case, for linear analysis, you can just use one. Perfect. So now, of course, one important thing is to keep the load constants for the subsequent steps. And of course, you want to reset the time step to 0 so that you can reuse the time series you defined previously for the next stages. Okay, now I will run this analysis just to show you that if you use the model subset command, you will not see the entire model, but only the pieces of the model that you specified using the model subset. Now, before running it, we need to do the mesh. Now, first off, we need to tell STKO that we want to use for all phase elements. We want to use a structured mesh with quadrilateral elements, okay? So assign and done. And then we want to use a seed defined by size, where the typical mesh size is 100. Okay, so this one will be my discretization. Done, and build mesh. Okay, so this one will be my mesh. So this is fine, let's save it and let's run it. Oh, here I have two versions of OpenSees. Now keeping the parallel from one side for the moment, because we don't need to talk about parallel analysis now. But I will use the default OpenSees installation. Then I will show you that there is a feature in OpenSees that it is not properly working in some scenarios, and we modified it, and I will show you how it can be done. So let's first start with the default OpenSees. I run this one. First stage. Now, of course, there is only one stage, one analysis, so it is fine. Now, what I expect to see is just my soil domain that is going down due to the self-weight. So exactly like this one in this first figure. Okay. So let's load. Let me move this apart. Let's go into Postprocessor. Also here, let's go into two-dimensional view. I don't need the grid here, so I can switch it off. Open database. Let me go into webinar, test 01, test 01. Okay. So the first thing that I want to do is to use a deform shape, switching off mesh edges and faces, and giving it a deformation of 0. So basically this one will show you the undeformed shape. And then on top of it, I will show a surface color map. Also here, I want to switch off mesh edges. And here I want to show you the stress state. So we can go into material stress. And for example, I can show you the principal maximum stress. And here we can use a deformation of, I think it was 10,000. Oh, just to make it more visible, I want to increase the soil domain of a factor of 10. In fact, you will see that in the example that you will see tomorrow on our website, self-weight of the soil has been increasing by 10 times. Not because it is a real number, just to have a proper visualization when I will put the structure on. Okay, so let me rerun it. Okay, and we reload it. Okay, so this one is the behavior that I expect in here. As you can see, the entire model is not in the domain, only the soil. Okay, now we can go into the second stage. So go back on the preprocessor. Now, basically, you have learned the first feature. In our previous webinar, we have never used the model subset command. And basically, if you don't use the model subset command, everything will be built since from the very beginning. But as soon as you use at least one model subset, then STKO will write or will send to OpenSees only the elements specified by that model subset. So for example, in this case, I never explicitly specified to add the frame structure, and the frame structure is not has not been transmitted to OpenSees. Okay, now we'll do the second step. I can clone this one. And what I want to do here is to create the second stage. I want to add the second piece of my structure. So stage 2, and it will be our frame. Okay, so I go into the selection set and I simply need to change from set 01 to set 02. Okay, now basically here we have our frame. Then we need to apply the load on this frame, but just to show you what's going on, I don't want to apply any load now. I just want to run a second analysis, once again, 10 steps without any further load, okay? So just this one. I clone it, add it, and I will clone this one, analysis 0.2, and press OK. Now let me save it. Now basically, what do you expect? As I told you before, this one Here I will show you a mistake, okay? So if you use this procedure, you add the first stage, then you let this first model deform due to a certain load. Then you add a second piece of the model. Actually, what you would expect is that this second piece, which has been added just after this load has been applied, you would expect that this frame structure here will not undergo any stress state. It will be stress-free because it has been added after the load has been applied. This is what we expect. But I will show you that if you just add an element in a plain way, just like I did now, it will not be like this. You will see what happened now. So let me run it. So first stage and second stage, okay? I will reload this one. Okay, so starting from the first stage, you will see that up to, here we are still at stage 1, step 4, up to step 9. This is the same thing as before. Then we move to the second stage, okay? Okay, now what's going on here? Basically, here I have a huge amount of stress in my column here, in my frame. And as you can see, it is not stress-free. Why it is happening? Because the soil was already deformed, okay? And basically, when you apply your structure, which was actually drawn up here, it will soon attach it to the previous nodes that were already deformed. So they went down here. And this structure is trying to adapt to the deformed configuration. Now, what happens now is that this foundation here is not stress-free, actually. Okay, so we can keep on going, and the stress remains like this, fixed. But as you can see, the structure is not stress-free. In fact, if I just select this piece here, actually, I need to show it. No, okay. Okay, it is not stress-free. So as I told you, this one is a mistake. You cannot just add a piece of the model onto another piece that is already deformed. Otherwise, the new one will deform rapidly from the undeformed configuration to the deformed configuration, and it will not be stress-free. So how do you solve this problem? Well, in OpenSees, there are two ways. So here that we are in the second topic of this webinar. What is the handle of initial strain field? Now, basically, whenever you want to add a new piece of model onto a model that has already been analyzed, we need to introduce the concept of the initial strain field. So basically, the superstructure will enter the domain in a deformed configuration, but in reality, that should be the initial configuration for my new model. And so it will be the strain field given by that initial displacement should not produce any stress. Now, this one it can be done in OpenSees, so OpenSees can handle it, but unfortunately, it does it in two different ways for solids and beams. So for the solids, there is the concept of the initial state analysis. While for the beams, there is no need to use it. You can just draw the beam as it is, and the beam will take care of removing the initial displacement, okay? While the solid does not. So for the solid, you need to use something which is called initial state analysis. Or at least this is what has been said in the different OpenSees tutorials. Actually, we'll show you that this one works, but it has several drawbacks, okay? And then finally, we'll show you a general solution that works both for solids and for beams. As I told you, now I will show you the initial state analysis. Keep in mind that it will work only for solids because it needs an ND material, and I will show you why. So let's start with this first approach. So go back to the preprocessor. And more specifically, we need to go to the property condition here. And we need to do some change to the physical properties. So the first change that we need to do is to use the concept of the initial state analysis wrapper, okay? If some of you is interested, we can go on the website and we can call OpenSees initial state analysis, and you will find an example here. initial state analysis wrapper. That basically is the material that we need for applying an initial strain field to something, okay? Here there is a little explanation. There are some notes. So already here you will see that there are some limitations. First of all, it works only for ND materials. This means that you can use this approach only for solid elements in 3 and 2 dimensions, but not for beams, for example. So this is the first drawback. The second drawback is that the initial state analysis, as they say, is somewhat tricky in dynamic analysis, and I will explain you why in details later on. And then there is actually this first problem, which is not a problem anymore, because here at the beginning they said that whenever you use the initial state analysis, all the previously defined recorder will be deleted. But this is not true anymore. I will show you that in this new version of OpenSees, there is not this problem. Okay. Okay, so perfect. Now, how do we use the initial state analysis? First of all, we need to go into physical properties, and we need to create an initial state analysis wrapper for each one of our materials. Okay. So the first one will be soil initial. We go under model, materials, and the materials, and material for what is it? Wrapper material for initial state analysis. Initial state analysis wrapper. So here it's very easy. The only thing that you need to do is to choose the original material, which in this case it is the soil, and then you just need to specify the dimension. If we are doing a 3D analysis, you choose 3, or you can choose 2. Okay. Now in my case, I choose 2. And this one will introduce a new error that I will show you later on. But let's choose 2 for this moment. Okay. And then I do the same. I just clone this one. And I change its name, and it will be not soil initial, but concrete initial. So the same 2 dimension, and I choose concrete here. Perfect. So now we need to change the material assignment. So I select everything that has the soil domain, and I drag and drop the soil initial. Okay. So basically, I'm replacing the previous selection. What previously had the soil material now had as the soil initial material, and I do the same thing for concrete. So select and drag and drop the concrete initial. Perfect. Now it's fine. This is only the first step because we need to do something else. As you can see in the OpenSees wiki, it is not sufficient to use the initial state analysis wrapper, but you need to use another command, which is called initial state analysis on and off. It is basically used to tell OpenSees that we are starting an initial state analysis. So basically the concept is just before running the initial state analysis, you call initial state analysis on, then you run the analysis, and then you use the command initial state analysis off. What this command will do is to store the initial strain given by the displacement field obtained by the first analysis, and this initial strain will be saved into the initial state analysis wrapper. Finally, this command will reset to 0 the current displacement. Okay, so basically you will end up with a structure which has a 0 displacement, but it has a strain field that corresponds to the initial displacement that has been obtained by this one. Okay, so basically if I go here, and how do you apply the initial state analysis wrapper? Well, actually in STKO we don't have a command for that, but every time you don't have a command, you can use the STKO script. So you can call this one initial analysis on. You can go under Michelano's command, custom command, and here you're free to write whatever you want. So in our case, we will write initial state analysis space on. This one will turn on the initial state analysis, and it will go just before the first analysis. Then I can just clone it. I move this one just after the initial analysis, and I will call it initial state analysis off, because I want to turn off the computation of the initial analysis. And in the script, I just need to write off instead of on. Pretty easy. Okay. Okay, now it is fine. Now we can just run the analysis, and what we'll see is that we'll basically see that the first stage will be exactly equal. So in the first stage, we will see that the soil deforms down up to step number 9 with this stress field. Then when I will move to the next stage, we will see that the soil goes back to the initial position, but the stress field will be the same. And this is due to the fact that we are using the initial state, the initial strain given by the initial state analysis. Okay. So here in the preprocessor, we can simply save it and run the analysis. Probably I wrote something wrong in initial state analysis. Yeah, the command name is wrong. Let me just copy paste it from here. Initial state analysis. Oh, I forgot the L. That's fine. So whenever you write a TICO script, pay attention that everything is written correctly. Now in my case, I forgot the L after the Y. Okay, perfect. Save it and run it. Okay, so first analysis. Okay, as you can see here, I have this extra string telling me that the initial analysis is fine. So initial state analysis on. Then STKO, OpenSees does the first analysis. Now at this point, my structure will deform. Then there is a call to the initial state analysis off that basically we store the initial strain and reset the displacement to 0. Okay, and then I will run the second analysis. Now the nice thing about this is that my soil domain will still have the same exact stress field because the strain field of the initial displacement analysis has been stored into the material. But the displacement is now reset to 0 so that when I put my new structure, it will not bend because it doesn't see any initial displacement, okay? And so this one will give me the exact solution, at least for this moment. Then I will show you that we are going to have some problems later on. So reload it. First stage. So as you can see, this one is exactly equal to what we had before. Displacement plus a stress field. Then when I go right to the second step, so I move from stage 1 to stage 2, you will see that now the stress state in my soil is the same, but the displacement has been reset to 0, and then I added my structure. Now basically here you will see nothing that is going to deform because nothing has changed, but my structure is actually now stress-free, okay? And this is what actually we expect from an initial state analysis. So basically now this one has been obtained using the concept of initial strain analysis. As I told you, the first drawback is that it can be used only with solids. The second drawback is that it is quite tricky. It's not explained very well, but in this case, I'm using the plane strain condition. If you want to use the plane stress condition, you need to do something different. And you will see on the file that I will send you tomorrow. But just to show you how it works, let me just show you how it can be done in plane stress condition. Why? Because by default, as you have seen before, I created a 3D material here. Then I told the initial state, oh, not here, the initial state material that my material was 2D. So actually, when you have a 3D material like here, like the elastic one, and you tell the initial state wrapper that it is a 2D material, there is a problem. It may ask you, what kind of 2D material do you want? A plane stress or a plane strain? Now, the problem is that this one is not documented, but if you just choose 2 here, it will convert the first material into a plane strain. Okay, I think we have a question. Yeah, the recording of this question, the recording of this session will be on YouTube, because we are actually live streaming on YouTube. So by tomorrow, you will find this one on our YouTube channel. Okay. So as I said, in OpenSees, the conversion of material from 3D to 2D is quite tricky, because sometimes it's done automatically, but sometimes it's not. So for example, if I use a three-dimensional material directly on an element, then I choose the element here and I choose plane strain, then this element will take this material and will try to convert it to a plane strain condition. And this is fine. If I choose instead plane stress here, if I choose plane stress, keep in mind that this will not work, because the element is trying to get a plane stress material, but there is the initial material wrapper in the middle. Okay, in the initial state analysis wrapper, I just said that I wanted a 2D material, and by default, it will try to convert a 3D material into a plane strain. So if you actually want to create a plane stress material, you need to, a plane stress material with an initial wrapper, you need to say that this one is a three-dimensional, okay? So the initial state material is 3D exactly as the initial material, so it will not do any conversion. Same thing here. I say that it should be 3. So it will not try to guess what kind of 2D material you want. And then you explicitly convert them into plane strain or plane stress. Now, in my case, I want a plane stress. So I can call this one soil plane stress. So as I told you before, if you want to do a plane strain analysis, there is no problem. If you want to do a plane stress analysis, keep in mind that this one is the procedure that you need. So original 3D material, initial state wrapper, and then you convert it to a plane stress. Because otherwise the initial state analysis will convert it to plane strain. So I take the soil initial and I convert it to plane stress, and then I do the same with the concrete. So I call this one concrete, plane stress, and I say that it will be the concrete plus initial state material to be converted to a plane stress. Perfect. Now I just need to select this one, and I drag and drop the soil plane stress, and select this one, and drag and drop the concrete plane stress. And then, of course, you go into the element property, and you say that you want a plane stress analysis, okay? So now this is just a little bit more tricky, but just remember that in plane stress cases, you define the element, the material, which is 3D. You define the initial wrapper, which is still 3D, and then you convert it into a plane stress, okay? But basically it is the same. Now we can run the analysis again, because of course there is a small difference between the solution given by the plane stress and the plane strain. Okay, but the results are pretty much almost the same. So reload, and here we are. Goes down, and then the structure remains fixed there. Okay, so this is fine. The form shape 1, 0. Okay, perfect. So now let's go back to our preprocessor, and now we are going to add a new piece to the model, which is the inner column. Okay, and now here I will show you the little problem given by the initial state analysis, which is not quite easy to fix. Okay, so let's say that now I want to add a new piece to my model, which is this initial column. So what do? I can simply clone the stage 2 frame, or actually, before doing this, let me add the load on the structure here. So I want to add a load, add weight, floor weight number 1. Because actually now I've done the second stage without adding any load. So I go to pattern, add pattern, load pattern. Still the ramp here. And here I want to just add the floor load number 1, floor weight. Okay. And of course, I need to bring it just before the analysis so that we can see also the deformation due to the frame structure. Okay. Go back here. Okay, now basically you will see the formation of the first stage, then second stage plus its own load. Okay, perfect. Now this is fine. Now in the second stage, you will expect the new column to be placed here, but the new column will not be affected by the stress, actually by the load applied on the structure, because it will be applied here in the deformed configuration, so it will be stress-free. Now let's see if everything is fine now. Let's see what happens. Now, first of all, as I told you before, if I simply add the third stage, like this one, I go here and I click on stage 3. Column. I go to the selection set as I did before, and I choose set 03 column. Okay. Now the column has been added. Now I don't want to apply the second floor weight. I just want to apply the first one, because I want to show you that even if I do not apply any further load, if I don't use another initial state analysis here, my column will undergo a compression stress state, okay? Because it will be applied into a deformed configuration here, where it will be compressed if I construct my column here directly into this deformed configuration. And this is not what I expect. So I clone this analysis, and I call this one analysis 03. Okay, it will be the same. Plane constraint, everything's fine. Okay. So I just run it. And third analysis. If I go here to the postprocessor, reload. So my first stage goes back to the initial displacement, and then I apply the vertical load of my structure. And then here in the next step, here I will add my column, but you will see now that my column is already in a compressed stress state. Okay, if I isolate my column here, for example, this is principal max, of course it will be 0. Let me go back to the vertical stress. Where is it? Okay, here the vertical stress is not 0. As you can see, it's a small value because I'm using very small loads, but it is not 0. It is not stress-free. Okay, and this is actually the same error that we have seen before, because basically we are adding this column without using another initial state analysis. So actually the solution here will be to add a new initial state analysis, but you will see that this one creates an error with the current version of OpenSees, and I will explain you why, but let's try to do it. So likewise I did before. So before the analysis number 1, I put initial state analysis on and then off. Okay, now in the analysis 2, I should do the same. So an initial state analysis on and off at the end. And then I expect that my structure will go back to its initial position, but now with the strain already stored also into the frame structure. But here you will see a strange behavior. So let me just clone this one. And this one can be moved just before analysis stage 2. And then I clone also the analysis off. Clone it, and this one can be moved just after the analysis number 2. Okay, so actually what I would expect now is to see my structure that goes down due to the soil deformation for the first analysis. Then it goes back to 0 displacement. Then it deforms due to the superstructural weight. in the second stage analysis. Then it goes back to 0 due to the initial state analysis off. And then I will see my deformation due to the third weight. Okay, now, in this case, there is no third weight, but I will see that my column has a 0 stress. Now here you will see a very strange behavior actually. And I will explain you why in a little. Second and third. Okay, as you can see, the second initial state analysis seems correct because as you can see here, before the first one, I see analysis on, initial state analysis off, then once again on and off. Okay, but actually we found a bug in OpenSees, and I will try to show you what's going on. So reload it. Okay, so first stage, deformation of the soil. Second stage goes back to 0, and now here I have the deformation of my structure alone. Now I expect this one to go back to 0, but as you can see now, it is not going back to 0. It is actually going into a positive displacement. Then I try to understand what was going on here. Actually, the problem is inside OpenSees. Now, the nice thing about OpenSees is that it is an open source software. So if you are able, you can go into the source code and see what is actually going on. Now, the main error was into this file, for those of you who are programmers. But there is the initial state analysis wrapper that basically stores the initial strain. Let me show you where, which is here, I think. Yes, here. This is a correct version because I correct my version. But if you can see before, and this is the change I did, before there was the initial strain is equal to itself plus the current strain, not equal, but it was plus. So what's going on is that if you do 2 initial state analysis, it will add twice the initial strain, okay? And if you do it 3 times, it will be even worse. So actually the change is very simple. I just did it. I will send it to Frank McKenna so he will update it in OpenSees. But for the moment, keep in mind that there is this problem, okay? And with this solution, actually it works because now I switch on my own OpenSees where I fix this problem. So I simply change the solver from OpenSees to OpenSees manual here, which this one is actually not the default OpenSees, which is this one, but it's actually a manual OpenSees that I compiled just today. And I think it will be online in a few weeks because I will send this problem to the OpenSees developers and probably they will fix it in a week or so. So I just changed the solver to the manual one. And let's see if something changes. Okay, so go back to the postprocessor and reload it. Okay, let's see what's going on now. So first stage, deformation of the soil. Second stage goes back to 0 and I have my structure, deform. Then once again, it goes back to 0. And then of course, now there is no deformation. I just want to see what's going on here. Okay, now as you can see, this one is actually in 0 condition. Okay, I'm visualizing the two, but this one is not deformed anymore. Show. But as you can see now, it's not going up. It has gone back to the initial state position, and this is fine. Basically, that was a very small bug, but it will be fixed quite soon. Now let's add the third weight, so our analysis is complete. And I just need to clone the floor weight number 1, and I bring it up just before the third analysis. Edit, and this one will be add floor weight number 2. And I need to change the floor weight to floor weight number 2. Okay, now we see a deformation also in the last analysis. So once again, reload it. first stage, second stage, and the formation of the only structure. Okay, so this is fine. Perfect. Now let's go back to the preprocessor. So as you can see now, also the third load is being carried by the 3 columns. So also this one now is going into a compressive stress state. Now this is fine, but as I told you, this one has many drawbacks. So the first one is that it is not unique in the sense that it can be used with solid elements, but what happens if you use beam elements or shell elements here? The shell elements and beam elements, they do not work with the concept of initial state analysis. So this is the first problem when you have to mix different element formulation. The second problem is the one that I just showed you. There is a bug if you need to do more than one stage. Now I easily corrected it, but it is not yet on the public OpenSees. So you may need to wait a week or so for the new OpenSees version to be out. And finally, there's a third problem. The third problem is already mentioned here, is that now it's doing a linear elastic analysis, a static analysis. But here in this case, as you can see, the developer says that there might be problems if you use dynamic analysis. Why? Because actually resetting the displacement to 0 is just a trick to avoid that the new structure will be placed into a deformed configuration. But if you look at the deformation here, you can see that it goes suddenly from a deformed state to an undeformed state. Now, as far as I'm doing a static analysis, this is not a problem. But if I was doing a dynamic analysis, this was actually a great problem because instantaneously the displacement will go from a value to another. And this one will actually create huge acceleration at that point, depending on the magnitude of the initial displacement. But since the initial displacement will be reset to 0 instantaneously, you will see probably some spurious oscillation in the accelerations. So for a dynamic analysis, once again, it is not useful when you use dynamic analysis, or actually it can be done, but you need to pay attention to the time step that you give. You need to do some intermediate analysis to dump out all those accelerations. So as I said, the initial state analysis works, but it has many drawbacks. And this one leads us to the final point of this webinar. There is actually a new solution that can be used with OpenSees, fortunately, which is very easy. You just need to change the way you do your model, okay, without using any initial state analysis. And I will show you how it can be done. I think it will take more or less 15 minutes. Okay. I will do it pretty fast, but you have everything in the second folder that you will find. So the first folder that you will find tomorrow on our website will be test 01 solid, which is this example using the initial state analysis. And the second one will be instead the one without the initial state analysis using what I called here kinematically constrained subdomains, okay, which is actually very easy. Actually, even easier than all these things because you don't need all the concept of initial state analysis. So let me save this one. And let's say, how do you convert this kind of model to a model that works with kinematic constraints? So let me save us a different name. And let's call it test 02. Okay, and I also want to change the name of the recorder here so that it will not overlap with the other one. So record 02. Okay, so let's do some changes. Now, first of all, as I told you, I don't need anymore the initial state analysis. And so I don't need the plane stress adapter because now I can just simply use the initial material here because it will be automatically converted by this one because there is no initial state analysis in the middle. So I select this one and I drag and drop the initial solid material. And I do the same for the concrete. Select, and I assign the initial concrete material. Okay, so now I can get rid of all this other stuff here. So as you can see already, the physical properties are much easier to handle. Then the material, the element is just plain stress. Conditions are the same, but the analysis stage are actually easier. I don't need to all the stuff of the initial state, so I can remove this one, and I can remove this one and this one. Okay, so I just need to create a recorder, add the first subdomain, add the boundary condition for the fixities, then the soil weight, first analysis, I add the frame weight, second analysis, I add a column, and I add the final floor weight, and then I do the third analysis, okay? But as I called it in this model, we need to do some change actually here. I call this one kinematically constrained subdomains. Why? You cannot do a single model like this. You need to split it into physically separated geometries, and you need to connect them through equal doffs, okay? Because fortunately, the equal doffs will work in a particular way that will make this application work quite easily. So how can you do this? I go in geometry. When you have a single model and you want to split it into subdomains, you can just click on it, click explode. Okay, so now I have a bunch of exploded faces, and then I will join them together pieces by pieces. So all of them and these two, they become a single geometry. So I can use the merge command here. Okay, and this single geometry here can be renamed and called, let's say, soil. Then I do the same for my frame structure. So everything but the inner column. Once again, I click on merge. And this one will be my frame. And the remaining one, of course, I don't have to do anything because it's just one face. I can rename it and call it column. Now, when you do all this operation, fortunately, STKO remembers the previous assignment, so you don't need to change anything. Also, the selection set are still fine. You can double check them, but they are fine. Okay, so the frame is still, the soil is still there, frame is still there, and column, it is still there. Okay, so the property are already assigned. Let's see the condition, and the condition are still there. Okay, so you don't need to change anything. You just need to split them. Now, of course, if you have split geometries like this, they will be discontinuous in these boundaries, okay? And so this model will be singular if you run it as it is, because the my structure will not be attached to the soil, and my column will not be attached to the structure. So I have three different pieces. How they connect them? As I said here, I will kinematically constrain them, okay, through equal doffs. So I will need to create interactions. Now, creating interaction on edges that are overlapping can be quite annoying. So what you can do is to actually slightly move this geometry, and then you will move them back. Okay, so first I want to move this one slightly down like this. And then I want to move this column here apart from here, okay? Just to be able to select the boundaries, okay? So now I create a first interaction, which I called it link 01. And it will be the connection between the soil and the foundation. So first of all, I need to select master geometries. And for master geometries, I will choose just the edges. I just need edges. All the edges down here, okay? Right click. And then I need to choose the slave geometry, once again, only edges. And I need all the edges of my foundation, which are in contact with the master edges here. And right click. Okay, now we see that all these points are connected here. All these points are connected to this point, but don't worry, this is not an error, because when you will move it back, they will be attached to the closest point, which will be now these ones, okay? So don't worry about this temporary drawing. And then you do another interaction that will connect the beam to the frame, the column to the frame. So link 02. Okay, and I will choose this one and this one as the masters. Right click, and this one and this one as slaves. Right click. Okay, now I can move them back to their initial position. I want to move this one back to here. Okay, so now you can see that the connection is on the proper position. And same thing for my entire, actually not my structure, but my soil. And I want to move it back to its initial position, which is here. Okay, so in this way, it's actually easier to create connection between overlapping geometries. Now, since I started from my previous model, it is still centered at 0. This is fine, but I want to slightly move it apart from here so that I can reload the results of this one, and there will be side on side with the other model, so I can do a comparison. Okay, so this is not necessary, but it's just to make a comparison. So I select everything and I move it from here to here. Perfect. Now we have everything, at least from the CAD model. We created these two interactions, but of course we need to assign boundary conditions to them. As I said, it's nothing complicated. We just need equal doves. So we go in condition, we go here and we choose add, and we call this one eDof. This one should be an equal dof for the link number 1, so equal dof between the soil and the foundation. So constraint, multi-point, equal dof to dimension, and I want to fix everything, okay? And this one will be assigned to the link number 1, which is this one here, okay? Perfect. Now I need a second equal dof to be assigned to the other link. So why am I doing two separated equal dofs even if they are equal? Just because of this, as I said before. If some boundary conditions are applied to different subsets, they should be modeled separately. Because in fact, in my second stage, I have only this frame structure here, but not the column. That's why if I applied equal dof at the same time here and here, it will give me an error because it will not be able to find the nodes of the inner column. So that's why I'm using two separated equal dofs. And this one will be the equal dof for the link number 2. Model, constraint, multi-point, equal dof. And it will be attached to this condition here. Okay, perfect. So we create these two conditions. Now we need to add them into the analysis steps. So we cannot add it here, as I said, because this one is still the first stage. So we need to create another model stage called add eDof 1 pattern, add pattern, constraint pattern. This one is a multi-point constraint, 1, and I choose equal dof link 1. And this one will go just after adding the second stage. So since basically this equal dof is trying to tie together the nodes from the soil and from the frame, it should be placed just after the frame has been added. Otherwise, it will give me an error if I apply it before. Okay, now I will do the same thing for the second stage just after the third stage. So I can clone this one. I edit it and I choose the equal dof number 2 this time. And this one, it will be moved just after adding the stage number 3, okay? So I add the column, and then I add equal dof between the column and the inner frame, okay? Then I add the second self-weight, and I do the analysis, okay? Now I just need to remesh it. Perfect. Let me save the model and run the analysis. So first stage, second stage, and third stage. Now, as you can see here, you don't see any string containing initial state analysis on and off because I simply remove them. Okay. Now let's see what happens in this case. So I go here, I open another database, which is on test number 2, called test 0. Oh, I gave the same name, but it's not important. Here I have the deformed shape, then I have the color map here, and then I want to add another surface color map, this time for the second analysis, okay? And so I choose the second database. So I want to switch off mesh edges, and I want to display the same stress state that I have here. So not displacement, but stress and number 2. Okay. Now, if I do an animation, and I need to use the same displacement, the same deformation scale. So this one was 10,000, and say 10,000 also here. Now let me just start them from the beginning so they will be synchronized. Okay, perfect. So next. Okay, so now as you can see, the first stage is exactly the same for both of them. Let me make some room here. Okay, I can get rid actually of the deform shape, I don't need it anymore. Okay, so the first stage will be the same. As you can see, the same results, same displacement. Go back to animation. So up to step number 7, 8, 9, 10. Oh, now the next one will change slightly. As you know, in the first analysis, I've been using the initial state analysis concept. So you will see that now this soil domain goes back to a 0 position, but keeping the initial stress. Okay. While in the second case, it will not move, but the foundation will be detached only visually. It is not important because the stress state will be the same. So the solution is the same. Keep in mind that you're working in small displacements. But the nice thing is that it does no drawback and it can be mixed with any other kind of element. Okay, so second stage. Second stage, this one goes back to 0, but the stress state is the same, as you can see here and here. Okay, and then you will see the displacement of the superstructure. Then third stage, once again, it goes back to the beginning. Here you will see that the column is detached, but it's not actually a problem. They are still undergoing the same stress state. The only difference is that this one is attaching through the kinematic constraint the displacement of the new model to the previous one only in terms of the delta displacement. So it is exactly the same model. As you can see, the stress state is the same here. There is no problem, and it is just more efficient. So the only problem is that visually you see a gap between them, but it's not a problem because, as you can see, remember that you're using small displacement assumption, so you can actually visualize it as a 0 deformation, and you will see no difference here. What you need to do in a small displacement analysis is just to take care of the stresses. Okay. So why now this version here is better than this one? Well, because this one has many drawbacks, as I've shown before. And the problem is that when you're, especially for people doing construction stage analysis, the concept of initial state analysis cannot be applied to beams. So the problem is that now in my case, I model the frame as solids, but typically this superstructure will be done with beams or shells. And in that case, it will not work. While this approach of kinematically constrained subdomains will work for any kind of material. And the other nice thing is that since here the displacements are not reset to 0 instantaneously, this one will work without any problem also in dynamic analysis. Okay. So keep in mind that you have all these possibilities, but I suggest you to review this one and use this one. First of all, because it's easier. You don't need to create the initial state analysis. You just need to create separate domains and the interaction between them. And finally, the equal DOF that connects them. Okay. So this is the main focus of this webinar. I think that this, of course, is not everything that can be said about construction stage analysis. There are many other things that can be said about this. In future webinars, I will show you how to do the same mixing solids, beams, and shell elements using the kinematically constrained subdomain approach. And I will show you another feature that can be very useful in construction stage analysis, that is the removal of pieces of domain. While in this case, I just show you how to add pieces of domain. But there is another feature that is available in OpenSees, but is not so easy to use. So that's why I prefer to keep it for a future webinar, which is the one of removing elements, okay? But it requires a little bit more knowledge because it's a little bit more tricky. So we'll focus on it on a new webinar. So for today, it's fine. We have everything. So if you have any question, we have about 30 minutes for questions. So please, if you have any question, we are here. We have 30 minutes for questions. And of course, could you show for 5 minutes a new post? Actually, it is still under, I can show something, but it is still under compilation. Just a second. In the meantime, please post other questions and I will, yes, I will just introduce, because actually in few weeks, we will release version number 2 of STKO, which has many new features. The most important one is the customization of the postprocessor. I will try to show you something. Let me just see if I have a compiled version for that, because we are still under development. Let me just have a look here. It is in a debug. Well, probably I can show you something. But let's go back to question and answers. We have some question here. Can we use the kinematic constraint for reinforced concrete in fill frame between measuring fill wall and RC frame? If yes, then it means we can model in fill wall by micromodeling, as you said, as you did last time for micromodeling, and just add RC frame by connecting the wall with the kinematic constraint off. Exactly, this can be done. This is one of the reasons why the approach with the kinematic constraints it's more useful, because in that case, probably you want to model the frame structure with frame elements and the infill with micro modeling. So probably in that case, you will have problem mixing solids or shells with beams. In this case, it will be very easy and it can be done. You can give it a try. Oh, so let me just share my screen. So this one was the answer for this question here. Let me go back to the questions. I need to stop my conversation here. Okay, first question. Now, actually, I would like to introduce just for a couple of minutes the new version of STKO. It will be available in a couple of weeks or so, but there are many new features. Let me just show you one of them, or a couple of them actually. Now keep in mind this one is still in a debugging phase, so it will be slightly slower, but it is not important. It's not the production code, this one. The first major difference that you will see from the previous versions of STKO, let me go back to full screen, is that now you have a new feature. So here, for example, we are in the preprocessor. You still have the work tree here, you have the terminal, the main window, but then you have something which is called scripting. So basically now you can script everything, both the pre and the post processor, using just Python scripting. Now we'll give you some example of how you can customize the post processor, for example. In the post processor here, the layout is pretty much the same. But you will find under the editor, you will find a menu which is script, so you can move from script to the editor. Let me show you how it works. So you can load any database. Now we'll show you not this one, but something on shells, which is very easy to show you one of the features that we have. Which is this one, I think, yes. Okay, so this one is a simple plate. I just want to show you one of the features that can be done now. Now, in this new versions of OpenSees, in the previous version of OpenSees or STKO, you could basically just see the results that you asked for in your recorder. So in my case, for example, I asked for force, section deformation, but also section fiber stress, strain, and damage. Okay, but these are the only variables that I've decided to use in my recorder. So basically, I don't have any results other than these ones. But now with the possibility of customizing the post-processor, you can actually write your own scripts. As you can see, this is quite similar to or simplified versions of MATLAB. You have a script explorer where you can save your folders. In each folder, you can save as many scripts as you want in Python, and then you can edit them here and you can run them. Now, basically, what I do here is just I import something from the STKO, which is this one, Python MPC, which are our library, and then we can interact directly with STKO. So for example, I can say I get the document, I run some command, I get some results, and I do some post-processing for that result. Now let me show you one of the main possibilities that you have. Now, for example, let me remove this one and let me go back to beam fiber color map. Oh, let me just remove these points, I don't need them. Okay, back to STKO. Okay, so now the first change that you can see is that now the fiber color map is more similar to the Gauss one, because now the fibers are drawn with the size which depends on the results, okay, which is more clear rather than it was before. If you want to go back to the previous settings, so everything at the same dimension, you can still do it here. Constant size, for example, and all the fibers have the same size. But now you can use other features. You can use, for example, min size at 0, so that you can see only the fibers that are more interesting to see, for example, in this case. Okay, now just to show you these new features of STKO, I want to go into constant dimension for the fibers, as we have seen in previous version of STKO. And here, for example, I'm showing the damage variable, okay? As you can see, this variable goes from 0 to 1. 0 means the material is not damaged at all, and 1 means completely damaged, okay? Let me make it slightly larger so it's easier to visualize. Okay, as you can see here, this one is bending due to a uniform pressure, and my shell is damaging, okay, in the middle here. Now, let's say you want to do some post-processing. I don't want to visualize the damage, but I want to visualize only the pieces of my structure where the damage is higher than a certain threshold. And it can be used, for example, to do some checks. Now, what I did in this script here is exactly that. So I get the document, I get a result, which is actually not this one, but is, or this one, but I need to change it. Get elemental result. So get a result on an element, and I want the result to be the damage. Okay. Then I say, okay, this one is the source result. So the result that you're already looking at here. Then I want to change it. I want to create a new result called virtual result, which is not a result that is stored into the database, but is computed by you. So you can enter any equation that you want. So in my case, I said, for example, I want this new variable to be damage damage larger or equal than 0.9. This one will give me a matrix of 1 and zeros. So 1 whenever the damage is larger or equal to 0.9, and 0 whenever it is less than that value. And to this matrix, I add another matrix, which is an AND logic operator between damage larger than 0.5 and damage less than 0.9, and I add them together. So basically what I will see now into the derived result is that I will see only 3 colors. So 0 for the damage variables which are less than 0.5, green for damage variables going from 0.5 to 0.9, and red for damage variable larger than 0.9. Okay, then I can give it a name. So for example, d larger than, oops, d larger than 0.9. Okay, and then I can give some components. I don't need this one, and I can add this new result to the database. Okay, once this new result will be added to the database, I will see it here. Okay, so let me run this one. As you can see now, I have a new result here, and I can go into the fiber color map, go back to the editor, and I can choose the other one. So not this one, but this one. And as you can see now, I see only 3 colors. I can see blue, where the damage was less than 0.5, green, where the damage is in a warning state, so between 0.5 and 0.9, and red, when my damage is over 0.9, so let's say a critical situation. So this one is one of the main examples that you can do with the new post-processor, but basically the possibilities are almost infinite because you can do whatever you want. So in this script, for example, you can take this result here, you can evaluate it, you can write plots, you can write reports, you can do whatever you want. You can export it in other softwares. So basically, once you have access to the document and to the database through Python, you can do actually whatever you want. This one is only one of the main options that you have, okay? So this one is just a small preview of what it can be done with the new version of STKO. Hope you will enjoy it, and when it will be ready, I think in a couple of weeks it will be online. All the new webinars will be about the usage of this new feature, of this new post-processor, because it will give us a lot of opportunity to inspect the results with more freedom. Okay. So let me go back to the questions. Okay, if there are other questions, please. Is it possible to do stage construction analysis using initial stress material and initial strain material commands? Which are the difference and which are the possible drawbacks? I think when you talk about initial stress, initial strain material in OpenSees, I think they are only uniaxial, but probably I'm wrong. Let me just double check it, because I think that in OpenSees those are uniaxial. But let me just check. It's not here. If I let me go back to physical properties, add material uniaxial, init strain and init stress. Yes, they are uniaxial. Actually, where is the question? Let me go back to the question. Okay, here. Yes, they are uniaxial. I'm talking about material used for truss and beams. So this is the problem. If you use the kinematic constraint, there is no drawback for initial strain and initial stress. The point is that the initial strain and initial stress for uniaxial are used for a different topic. So for example, if you are if you are not analyzing for the initial stress, but you already want to give it an initial stress, okay? The kind of stage analysis that I'm saying here is that you first do the analysis, and then the initial state analysis wrapper automatically assign the current strain as an initial strain. But the things that you're saying is actually is the user that gives the initial stress or initial strain. So it should not be there should not be any problem with the kinematic approach. Using kinematic constraints, as I shown before, is perfectly fine. There is no drawback with any other kind of material. So of course you can use them. Okay. So is there any other question? Will the new version still be automatic update for those having licensed one? Of course, it will be available for the ones with the previous license, because the STKO licenses are subscription based. So basically you pay the subscription every year, and that is the main advantage of having a subscription based license, because every time you have a new version, you can just download it. In fact, when the new version will be available, you can just download it, but you can do it already now. For example, if you have version 1.1 and now we have version 1.4, you can just download the new version because the license is attached to the customer, not to the version of STKO. Okay, so in the year that you pay the subscription, you can update STKO as many times as you want. So there is no restriction on that. Okay, any other questions? Okay, if you have other questions, we have other, let's say, 10 minutes. Okay, so if there is no other question, I would like to thank you for taking part in this webinar, and hope to see you soon in the next webinar, which will be in a month from now, and it will be about model analysis and response spectrum analysis in OpenSees and STKO, and it will be improved for sure. Before the next webinar, the new STKO version will be released. So we will use the new STKO version, and I will take advantage for introducing more of the features of the new STKO version. And from then on, we'll basically do almost all webinars in this year, taking advantage of the customization of the post-processing tools. So we will show you how you can customize your results, how you can write reports, how you can export data to Excel in a programmatic way, and all this stuff. So thank you, everyone, and see you soon in the next webinar. Okay? Thank you.